And then we are going to now try to fix again SIDH. So the first one is going to be masking SIDH. It's with Tomoki.
Okay. Hello, I'm Moriya, and today the presentation is the masking SIDH. Where do we stand? And first, I explain what was our research goal. As you already know, the attack from the Castryck-Decru and Mino and sorry, I'm sorry. I remember the before the 1 minute ago, but I forgot now. I'm sorry. Leuven attack broke the SIDH, and then these three attacks all use these two information. The first one is the torsion point information, and second one is the degree of the secret isogeny. So in this work, we try to do something to these informations and prevent the CDMMR attack. More precisely, we propose the two countermeasure candidates, Masked-degree SIDH, MD-SIDH, and masked torsion points SIDH, MD-SIDH. And we propose the security analysis of both schemes and mention further analysis. Okay, then here's the table of contents. And first, I recall of the CDMMR attack. And as you already know, SIDH is broken in polynomial time. And here is an important algorithm. And this is a version of the Castryck-Decru attack, but it is a very similar algorithm used in the other two attacks. First, we compute the C, this C, and compute this isogeny of degree C, and compute these points, and compute this D. And if D is a product of FD curve, and it outputs true, and it's not a product of FD curve, it outputs false. And this algorithm finds the direction of the secret isogeny. And the important part is the first one is line 1. Then we use here the information of the secret degree of secret isogeny. And second part is in the line 4. And to generate the kernel of this isogeny, we use the torsion point images in line 4. So there is two information to use this attack. First one is the degree of the secret isogenies, and next one is the image point of FQ. So we first present the Masked-degree SIDH. It is highest degree of secret isogenies. And second one is masked torsion point SIDH. It hides the image points information. So then I explain about the construction of the Masked-degree SIDH. And this is the main idea for the Masked-degree SIDH. The most important part is use a P, like a form of like this, and L1 to LI dot LT to LT, and dot P1 to B1 dot PT to BT dot F minus 1. It is inspired from the prime of the C side. And we then these L1 to LT and Q1 to QT are distinct small primes. And we denote the product of Li to AI by A, and then the product of Qi to Bi by B. And here's the next point. As computes the product of Li to AI prime isogenies. Here, AI prime is the integers in the 0 to 80. So there can be a lot of degree for the secret isogenies, and the size of the space of degree is product of AI plus 1, product of AI plus 1. However, the pair pairing leaks some information of the degree. From the equation, it leaks the degree of phi A modulo B. So we need to randomize the image point by some random value alpha. And then here's the precise construction in the probability generation. And first, I'll just take this vector AI prime to AT and I generated on the by alpha and KA. And she set the A prime as the product of AI to AI prime. And next, she computed the point array like this. So the order this point become the AI prime. So this is a hidden degree of SIDH isogeny. And she computed this probability, and then the points become randomized. And this is a probability, and this is a secret key. And this is the construction of the Masked-degree SIDH. And for Bob also do a similar to way, and finally they key exchange and same way to the normal SIDH. And next, I introduced the problem for the Masked-degree SIDH. Here's the setting of the Masked-degree SIDH, and let phi is isogeny from E0 to E be a uniformly random isogeny of degree A prime. And the problem is the given E0, P, Q, EA, and P prime defined by this, and Q prime defined by this, compute phi. This is a problem for the Masked-degree SIDH. Okay, then Masked-degree SIDH, this is the construction, the Masked-degree SIDH. Is there any question about the Masked-degree SIDH? Okay. Then next, I explain the mask torsion point SIDH. And this is the main idea for the mask torsion SIDH. First, we set P like this. This is very similar to the Masked-degree SIDH, but the exponent is 1. And I will compute the AI isogeny. It's the fixed degree. So the degree space is not so big. It is only the one element. And I will sample the random value alpha and compute these 2 points. Do you think the wave pairing reaches the square alpha squared mod B? But it is okay because the number of solution of the x squared equal alpha in z over bz is 2 to t. It is proved from the Chinese reminder 7. So when we set the t equals lambda is the security parameter, the space of the alpha becomes the 2 to lambda. So it seems secure. And here's a precise construction of the mask torsion point SIDH. First, I'll take the alpha, and then she also take the Ka, and she computes array, and finally she computes this value, and by using alpha, she randomizes the torsion points. And this is a construction of the mask torsion point SIDH. And it also do the Boris the same way, and we can do key exchange by using the same way to the original SIDH. And finally, I introduced the problem of the MSIDH. The first one did a setting for the MSIDH, and let the phi is the isogeny, uniformly random isogeny from E0 to E and of degree A. And the problem is given E0, P, Q, EA, and P prime, Q prime, compute phi. Okay, so
do we have it? So we're just going to switch speakers. Do you have any questions
about the nothing? Okay.
Oh, wait, we have one here. No, I think you can. Then I pass the microphone to you.
So the question is, isn't the second one contained in the first one already?
Yeah, the first one is okay. You mean the first one? You take the randomized. Okay, we are sure. You say the first one is also the randomized, so it contains the second one. You mean? Yeah, it is. Yeah, it is true. But yeah, in this presentation, you will know that the security is not difference between the MD-SIDH and MS-SIDH. So that these are the inside the security, they're essentially same.
Maybe
it's okay.
just to complete his answer, I think they may look similar, but on one side, you really want to hide the degree, while on the other side, the degree is really fixed. And this makes a huge difference in practice. Like you are really hiding the degree on the other side. And it's just that we didn't include the parameters, but for the parameter choice, you will see that you cannot use the same T. For the parameter suggested in the max degree, you have T, which is like lambda over 2. But here for max torsion points, you must have T equals to lambda from the beginning. But the main idea is like hide the degree, and the other one is like hide the torsion points. So
Great. And then we go to the second speaker, the Tako Boris, which is also attempt to save SIDH.
okay, I hope we will still be optimistic at the end of the talk. So where are we? Okay, he moved back to, oops, I'm too far. Okay, so thanks Tomoki for the first part. I'm now going to talk about the second part, which is analysis. So we will start by the max degree 1. And we recall that in the max degree problem, you have this A, which is L1 to the A1 and LT to the EA, and you have B, and you have an isogeny of non-fixed degree A prime, and you also have the image of torsion points up to a scalar, and you want to recover the secret isogeny. So what the results that we have here till now are the following. One can efficiently recover the square free part of the secret isogeny in practice. And the second thing is, when you know this square free part, you can in fact reduce the max degree into an instance of max torsion points. So these are the two results that we have for this part. And let's start by saying, how do you recover the square free part of the degree? So if I have the integer A, which is of this form, if I suppose that the integer A prime is of this form, then I just take the exponent. I write the exponent of this form, then I can like extract the exponent of an integer by applying this A to the integer, or I can, from the exponent, I can recover the integer by, as it is defined on the slide. Then you can like look at this characteristic, this key that just tells you if an element is a square modulo Qi to the Bi, not that Qi to the Bi are the prime powers factors of B, the Bob's isogeny degree. So with this, you can define this map phi that goes from Z over 2Z to the T, and that just tells you if the integer whose coefficients are A prime is a square modulo each Qi to the Bi or not. And one thing is that you can in fact evaluate this map on the secret isogeny degree. So not the secret isogeny degree, but the secret isogeny degree reduced modulo 2, like each component reduced modulo 2, and this corresponds exactly to the square free part of the degree. Because here you are recovering the exponents in the degree, like these exponents modulo 2. So this corresponds exactly to the square free part of the degree. So why can you evaluate this on the degree? Because in fact, with the pairing you have, alpha square A prime, but everything which is square is like in the kernel of this map. So this evaluating this map on alpha square A prime would like give you the value of the image of A prime itself, and that is the image of the exponents modulo 2. So when you recover alpha square A prime through the veil pairing, you evaluate this map on this integer, and then you will get the image of AI prime mod 2, which gives you the the image of the square-free part of A. So when you evaluate the map, then since it's a group morphism, when you know the image of an element, then you can get this element up to the size of the kernel in general. So what happens now is, what we need to know now is the size of the kernel of this map. If we know the size of the kernel of this map, and in particular, if the map is an isomorphism, then it means we can recover the square-free part of the degree. Is it okay? Yes, it seems. So what is the size of the kernel of this map? There is one old theorem, but not by Kennedy this time. So there is one old theorem that says that if you take a random matrix over F2, then the rank of this matrix, you don't expect it to be smaller than T minus 3 in general. So the rank will be smaller than T minus 3 in general. But for our case, we are the one choosing the primes, right? So it's not really like the map of phi is a random matrix. But if you try to understand what it means that the kernel is very large, what does it mean? It means that square-free integers are like squares modulo, let's say t different prime powers. And in practice, to build this type of integers that are all divisors of A and that are squares modulo a chain of t integer, we call that t here will be like lambda over 2 or lambda for the max torsion point case. Then this becomes very hard in practice. And when you try to build this type of integer, if you try to make the distribution to build the LIs and the QIs in a biased way, then you will get parameters that in practice you cannot even try to use them. Like, yeah. So this constraint is a lot, and trying to satisfy this type of constraint, you will get parameters that are really, really large that you don't even want to build a scheme with it. So with that, we believe that in practice, it will be very hard to come up with parameters that for which the rank of the matrix is larger than T minus 3. So at the end, you will always have ranks, matrices, or the rank of the map phi, which is at least T minus 3. And this means that, in fact, the size of the kernel is about 2 to the 8 elements, 2 to the 3 elements. And this was, in fact, the case for the parameters suggested in the paper by Moriya. And for those parameters, I think T was either 1 or 2, depending on which degree you are looking at. So what does it mean? It means that for those parameters, for example, we can recover the square-free part of the degree. Is it okay? Yep. Oh, sorry. So now what happens when you know the square? What happens when you know the square-free part of the degree? What we show is that you can in fact reduce into a max-degree SIDH instance. Oh my God. Okay. Maybe I should hold it like this. So what we show is that if you know the square-free part of the degree, then you can reduce it into a max-degree instance. So assume that you know the square-free part A1 of the degree, A1 dash, of course. Then you can look at the max of n's such that n square AI prime is still smaller than A. So you have this secret degree, you have the square-free part, then you have a square part which is left that you don't know. In fact, you know that your degree A prime is A1 prime times some square part that you don't know. Let's say A0 prime. But you can complete this square part to get something which is very close to A. So you can multiply this by some, let's say alpha 0 square, or this is a square here, to get something which is smaller than A, but that you don't have anything further like. And this is what we will show, that you can efficiently recover this element. And this is in fact the element you have here. This element will be given by n square A1 prime. So if you set A0 to be the max of these elements, then you have that there exists an alpha 0 such that this quantity A0 square A1 dash equals to alpha 0 times the secret degree that you don't know, and this is still smaller than A. But the thing is that you can in fact find the this, you know this integer. And why? Because you know the square free part. Since you know the square free part, then you know this NA. And then you can just consider the isogeny phi 0 equals to alpha 0 times phi. Then the degree of phi 0 is it is NA and it is none. So now you have P prime and Q prime, and you know that they are alpha phi P, alpha phi Q. Then you can just put alpha 0 minus 1 and alpha 0, and then you get that these are exactly the images of phi 0 P, phi 0 Q scaled by this integer. But you can also recover the square of this integer by just doing this little computation. When you do this little computation, you get the square of this integer, and then sampling a random square root, you know that this random square root will be some square root of the unity times the original square root that you are looking for. And then just with a little simplification, you get that when you scale these points by alpha 1 prime, alpha 1 prime, okay, then you get mu times the phi 0, where mu is a square root of 1. So now you have this phi 0 for which you know the degree, and you know the torsion points up to a scalar. So this means you have an instance of max torsion points, in fact, with a little difference that it's not cyclic, but I'm not sure there is any problem with the Castryck-Decru attack in this case. So that's it. What does this imply? This implies that if you can recover mu, then you can break the thing, because then you know the mu, then you know the exact torsion point information. Hence, you can try you can go through all different values of mu. And going through all different values of mu, you have t to 2 to the t possibility. So you have an attack in complexity 2 to the t. And in the parameters suggested, t was equals to lambda over 2. So this means that those parameters were not secure. And this also implies that you would need t to be lambda, like in the max torsion point, max torsion points case. You would need to set t equals to lambda. And recall that in the max degree case, you have exponents in the LIs. So this means the parameters will be larger compared to the parameters in the max torsion point case. So in general, one needs t to be lambda, and yeah. And also, since we have done a reduction, then any attack that applies to the max torsion point case is likely to apply to the other case as well. All good? I see people getting sad already. They thought I was going to say SIDH. We are not yet there, I think. It's still like a long way. So this is for max degree. Now let's look at max SIDH. And yeah, the news is not good as well. So what is the problem here? The problem is that you have A equal defined this way, B defined this way, and then you have the same setting as before. Then you are given the images of torsion points up to a scalar. Then you want to recover the secret isogeny. So what we have here is that if you know a small endomorphism on the starting curve, then you can still run the Castryck-Decru minor martingale-robert attack in polynomial time. So how does that work? I think people on the torsion points attack can already know what I'm going to talk about here. So the main ingredient here is one thing that was added to Damien's ePrint few days ago. And it was that the attack applies when the degree, so the degree of your isogeny is like the square of the amount of torsion points you have. So you don't need that, you don't need NA to be greater than NB. It's sufficient to have NA squared greater than NB to run the attack. So yeah, so now the attack has exploded a bit, yeah. So this is really frustrating when we knew about this, because someone told us that go and look that paper, it has changed, and we went and looked, and it was like, oh my God. So with this, you can already see what we are going to do. Lollipop, as always with torsion points attacks. So if you don't know what a lollipop is, then you can look at this. It's not the Leuven lollipop, but it's the normal lollipop. So you have E0, you have an isogeny to EA. A lollipop means you take something here, theta, and then you come here, phi dual. What you do is that you have an endomorphism here. So the lollipop is, you compose, oops, sorry. What have I done? You compose phi A dual with theta with phi A, and then you get an endomorphism on EA. What is the degree of this endomorphism? The degree is the degree of phi A squared times the degree of theta. So it's roughly the square of the degree, but as I told you before, Damien Robert said that the attack still applies even when you have this. So even with the B torsion information, if you can like evaluate this isogeny on torsion points and get the exact torsion point image, then you can still apply the Castryck-Decru attack. So how do you see that you can get the exact torsion point image? Remember that in the Masked-degree, you only scale the torsion points by a scalar. But here, the isogeny phi A comes twice. So when you do this composition, the scalar would appear twice, and then you will get the square. But with the pairings, you know the square. So you can like erase the square from the equation. Then you get the exact torsion point images. In general, you can always choose the alpha to be a square root of 1, as we saw before, so it will even just go away by itself. You don't need to like do anything else. So then when you have these, since Damien Robert said that you can run the attack with square degree and square root amount of torsion point information, then you can still run the attacks. That's why we need the degree of theta to be small, because if the degree of theta is very large, then you will not, the degree of this isogeny will be considerably larger compared to the amount of torsion point information you need. So yeah, when you do this composition, the magic happens, the scalar goes away, and then you get your exact action on torsion point images. So what does this mean? As I said before, if this is smaller than B square, this is the degree of your isogeny. And as I said, you need only half of square root of torsion point information. So if this is smaller than the amount of torsion point information squared, then you can run the attack. If not, what you can do is like the tricks that you have seen in the 2 slides yesterday. You can always like try to guess part of the isogeny, or you can also try to guess new torsion point information to reduce the gap between the two. But guessing torsion point information, I think, is more costly. It's better to just guess part of the secret isogeny. After that, when you guess, for each guess, you then still run the attack, and then you'll probably get away with it. So if you look in the general case, then if I want to guess part of the isogeny here, since there is a square, then I need to guess an isogeny of like square root of degree of theta. Then it means in general for M small curves, as far as you can evaluate the endomorphism theta, you need the complexity will be roughly O of square root of M, ignoring any polynomial factors or anything that can come which is small. Then with the reduction of Masked-degree SIDH to MSIDH, the lollipop thing extends also to that case, and yeah. So I think that was it. And to conclude, so we presented 2 countermeasures and we provided some advanced analysis, and the outcome of the analysis is that the MD-SIDH can be reduced to M-SIDH, and there is a lollipop attack that breaks both schemes when you know small endomorphism of the starting curve. Oh my God. So as a consequence, any instantiation requires for now, okay, this, you shouldn't like take this as, you shouldn't read this like, as a consequence for now that I'm speaking now, any instantiation will require a starting curve with unknown endomorphism ring. So the right thing is, in the last in summer we saw that going to higher general solves everything. So with going to higher general solve this one, like the thing is, it's not really the same thing. Like you really want to have a lollipop, and the morphisms that Damien has in higher dimension, they are just matrix of scalars. And when you use this, it seems like you always get your scalar multiplication. You don't really get the effect that the endomorphism should really like offset the torsion points as you really want. And at the end, you also really want to have phi and phi dual so that you can remove the square of the scalar. So if you have only phi in when you compose both, or if you have only phi dual, then you don't remove the scalar, and it's really hard to see if we can come up with is it trivial or non-trivial? A trivial or non-trivial endomorphism in higher dimension that you can use to obtain the lollipop here. So I think that's it, and thank you for your attention.
So we have questions after this very like kind of pessimism talk, or someone has questions? Yeah, we have one question.
Thank you for the talk, both. So on slide 15, Boris, you said something slightly more hopeful than you said in the conclusion slide, which was the MD side likely reduces to the M side problem.
Sorry, which slide?
Here, yeah, last bullet point.
Yep.
Oh, sorry, other way around. So is the word likely just you being very careful, or is it coming from maybe you can very carefully construct some parameters where that rank condition doesn't hold, or?
I think maybe likely is just being mathematically careful.
Oh, you're just being careful. Okay. So it's not actually hopeful.
For me, no.
Okay, I tried.
Yeah, okay.
Did you calculate the what parameter sizes? Something? Did you do something about the?
Yeah, there are parameter
Yeah.
sizes online, in fact. But
Okay, yeah,
those-
and it's not very hopeful, right?
the Masked-degree one is for the ones that are online are broken. All of them are broken because you start from E1728, which is the daemon in isogeny-based cryptography. But yeah, so you need to have a random starting curve for now, as I said, for now. If you have a random starting curve, then in the Masked-degree, you need T to be at least lambda, which like says, okay, maybe you should just use max torsion points for now. And yeah.
You mentioned that you need an unknown endomorphism ring curve as a starting curve, right?
Yeah.
But what if you do know the endomorphism ring, but you don't know any small endomorphism in it? Like if you start from 1728 and take a long walk and you use that.
Yeah, it's probably also an option, but yeah, maybe having going to a starting curve with unknown endomorphism, which is very costly now, is not the direct solution. That is a valid solution. I thought about including it in the slide, but at the end I said I don't want things that would still bring more cryptanalysis. I just, but it's a valid, very good point. Thank you.
Wait, we have one question there. People really want me to walk.
If you pick the parameters now, like T equals lambda, then like roughly what would be the bit size of the base field that you're working over?
6 tau for T equals lambda. For Masked-degree, T equals lambda over 2. The size was already 6,000, I think, 6,000 bits. But for max torsion point, it was 3,000.
Okay, thanks.
Any other question while I'm here looking easier to reach? Okay, So I don't think we have any other questions. Well, we still have 1 weekend to go. So if you push more parameters, I think people are going to have some nice weekend breaking it.
Okay, thank
So
you very much.
there's one comment from Damian Robert in the Zoom chat. He says he thinks you can maybe use a lollipop-like endomorphism if you have a small degree isogeny from E to E prime, if you are able to push forward via the unknown isogeny somehow.
I didn't get the thing. Maybe I have to draw it to understand what, like, no. Is it, I read all the messages or I read only?
Damian, if you want to talk to Boris, you can
Yeah.
also unmute yourself. I think we should be able to hear you.
Maybe
He
he's not
doesn't have a
hearing me.
microphone.
Ah,
Well, then in that case, maybe we can also discuss afterwards.
I need to do a construction to check if it works anyway. I will send you an email.
Okay, there's
Thank
gonna
you.
be an email, I see.
Yeah.
Okay.
It's going to be a nice weekend.
Yeah.
Okay, so let's just talk both speakers again.